Okay, so in the previous section we talked about the convolution theorem, which shows us how to find the Laplace transform of a convolution pretty simply. To show how useful this theorem is, we're going to do a Laplace transform of a convolution of two relatively simple functions, cosine of 2t and e to the t. And we're first going to do it without the use of the convolution theorem, which is going to be a somewhat lengthy process, and then we're going to use the convolution theorem to confirm our result, and it's going to be massively faster. So for this, let's go ahead and start with the definition. Let's find the convolution first, and then we'll apply the Laplace transform to it. So what is the convolution of cosine of 2t with e to the t? Well, by definition, that's the integral from 0 to t of cosine of 2 tau times e to the t minus tau d tau. Remember, it's f of t times g of t minus, it's f of tau times e to the t, g of t minus tau dt that we're integrating. So because I'm integrating with respect to this tau here, t is being treated as though it were a constant. So notice I could take the e to the t that would be a factor in here and take it out of the integral. This is equal to e to the t times the integral from 0 to t cosine of 2 tau e to the negative tau d tau. Okay, now the next thing I would have to do here is do some integration by parts, and I'm going to skip showing u and dv and du and v and all that stuff, and just go to what this would be. But I will mention what I'm choosing as my u and my dv. So e to the negative tau is going to be my u. Cosine of 2 tau d tau is going to be my dv in integration by parts. And what this will end up looking like is e to the negative tau sine of 2 tau over 2 evaluated from 0 to t plus 1/2 integral from 0 to t e to the negative tau sine of 2 tau d tau. Okay, now this first term right here, notice that my lower limit of integration, sine of 0 equals 0, and that part will go away. Plugging in my upper limit of integration, t will give me e to the negative t sine of 2t all over 2. But this e to the t out here, when I distribute it in, will cancel with that e to the negative t. So what I'm left with here is 1/2 sine of 2t. Okay? I would also have to distribute that e to the t into this term. So this becomes plus 1/2 e to the t times this integral. But this integral also is going to require integration by parts. So once again, I'm going to skip the all the labeling of u and dv and all that, but I will mention that I'm choosing e to the negative tau as my u again, sine of 2 tau d tau is my dv. So in this case, what we end up with is negative e to the negative tau cosine of 2 tau over 2, and once again evaluated from 0 to t, minus 1/2 integral of from 0 to t e to the negative tau cosine 2 tau d tau. Okay, and then evaluating this at my limits of integration here. So plugging in a t, I'm going to get negative e to the t, e to the negative t cosine of 2t all over 2. I'm going to take this 1/2 here and bring it out to this guy to make it a 1/4. So let's do that. I'm going to have 1/2 sine of 2t plus I'll have a 1/4. Okay, and then if I distribute that e to the t in, when this becomes e to the negative t, that will cancel with that, and that's going to leave me with 1/4, negative 1/4. Sorry, that should be a negative. Cosine of 2t And then plug my lower limit of integration in, my entire numerator becomes a 1. So this becomes a minus 1/2. I'm subtracting a negative 1/2, which gives me a plus 1/2. But then I have to distribute this other 1/2 and that e to the t into that. So let's actually make that a 1/4 e to the t. I'm doing a whole lot of algebra that I'm just kind of talking through. But hopefully you're comfortable with that. And then I have this guy right here. So this integral looks similar to what we have here. But notice I have to multiply this 1/2 e to the t into this. Now the 1/2 times this 1/2 is going to give me minus 1/4. And the e to the t, I can actually multiply all the way inside to this integral because, again, t would be treated like a constant here. So this becomes the integral from 0 to t of e to the t minus tau cosine of 2 tau d tau. And if you notice, this integral matches this integral. So treating this as an equation now, this equals this, I can add this term over to this integral, which gives me this. 1/4 plus 1 would be 5/4. This would be 5/4 times the integral 0 to t cosine of 2 tau e to the t minus tau d tau equals 1/2 sine of 2t minus 1/4 cosine of 2t plus 1/4 e to the t. Now I can multiply both sides by 4/5, and I'm going to keep a 1/5 out and also recognize that this integral is the definition of our convolution. So I'm going to have cosine of 2t, its convolution with e to the t is equal to 1/5 times the 4 that would get distributed in here is going to give me a 2 sine of 2t minus cosine of 2t plus e to the t. Okay, so this would be just the convolution. Look at all the work it took just to get to that convolution. And I even skipped a lot of algebra just by talking through it. So this could have even looked worse. And we're not even done with the first step of our process, which is to find the Laplace transform of this. So now I need my Laplace transform of the convolution of cosine of 2t with e to the t. Taking the convolution of this side, noticing that the by linearity, the 1/5 can be brought completely out to the front the way that it is. I'm going to have this sine of 2t minus Laplace transform of cosine 2t plus the transform of e to the t. Okay, now all of these Laplace transforms are easy because I know them from my table. So this would be equal to 1/5 times, okay, so sine of 2t, its Laplace transform would look like 2, because that's my k, over s squared plus 4. But then I have this other 2 right here that's being multiplied to it, so that's 4 over s squared plus 4. And then this guy would look like minus s over s squared plus 2 squared, which is also 4, plus the Laplace transform of e to the t we know is equal to 1 over s minus 1. Okay, this, of course, if we wanted, we can combine this all into a common, or into a single rational expression. So getting a common denominator, which would be s squared plus 4 times s minus 1. I need to multiply by the correct factors to get my common denominator. I would have 4 times s minus 1 minus s times s minus 1 plus 1 times s squared plus 4, all over that common denominator of s squared plus 4 times s minus 1. From here, distribute things through the denominator or the numerator. You're going to notice that a lot of things cancel out, and I'm left with this 1/5 times 5s over s squared plus 4 times s minus 1. Finally, I can cancel these 5's out, and I get a final answer of s over s squared plus 4, s minus 1. So about 10 minutes later, we have an answer, okay? And that was the Laplace transform of a convolution of those two functions. All just to get this. Now, let's use the convolution theorem. You ready? Convolution theorem. So we have our convolution up here. The Laplace transform of cosine of 2t and its convolution with e to the t, according to the convolution theorem, is equal to the product of the Laplace transforms of each of those functions separately. Cosine of 2t times the Laplace transform of e to the t. Okay? Laplace transform of cosine of 2t, we just did that. We know that it's equal to s over s squared plus 4. Laplace transform of e to the t is equal to 1 over s minus 1. Multiplying those together, s over s squared plus 4 times s minus 1. Took less than a minute. Okay, so that's how powerful this theorem is. Look at all the work that it would have saved us if we just used that convolution theorem from the very beginning. So we won't be going through all of this anymore. You will in the homework, but we now have a very useful theorem. One thing I want to say before we move any further, we evaluated a differential equation in the last section, and that was the only differential equation I'm going to be doing in these lecture notes. Even though more appear in the book, there's a couple of things that we're skipping in this section. So if you continue on in this section from where we are right here, they're going to introduce you to things called integral equations and integro differential equations. Integro differential equations, which is fun to say. What those are, it's like the integral version of a differential equation. So remember, a differential equation is an equation involving some function, we call it y, and some of its derivatives, maybe a y prime or a y double prime, or any number of derivatives. So the function and its derivative are showing up in that equation. An integral equation is an equation involving a function and an integral where the integrand involves that function somehow as well. And in your book, you'll see examples of that in this section. An integro differential equation is a mix of an integral and a differential equation. So it's an equation involving some function, let's call it y, or let's call it f of t, because that's how it's going to appear in your book. And mixed into that equation will be derivatives of f of t, as well as integrals involving that f of t in the integrand in one way or another. Okay, this would be the only section, I believe, in this book that we would be encountering those types of equations, and only in very limited capacity. It's not really a major subject for this course, so we're not going to be doing any of those here. I just wanted to mention that because that's kind of the primary place where the convolution theorem shows up and is useful in the solving of equations. But what we're going to be doing is just working with some properties of Laplace transforms. So we're not actually solving any more equations in this section. We're just working with these operational properties. Okay? Now, in our convolution theorem, if we were to take, let me go back to that theorem so we can use it for reference. Find the page that it was on. If we were to set g of t equal to 1, then the convolution would look like this integral, right? Because g of t minus tau, which would be showing up in here in this integrand, would just equal 1 anyways, and so it doesn't need to be written. So the convolution of f and g, where g of t is equal to 1, looks like this integral right here. And according to our convolution theorem, the Laplace transform of that convolution would equal the Laplace transform of f times the Laplace transform of g. But because we know what g is specifically, namely the function 1, we can find its Laplace transform directly. The Laplace transform of the constant function 1 is equal to 1 over s. So all that is to say is that the Laplace transform of that convolution, which just looks like an integral from 0 to t of some function f of t, is equal to the Laplace transform of f of t over s, from this 1 over s right here, okay? With that comes the inverse Laplace transform. The inverse Laplace transform of any function over s can be turned into an integral in this way. And so this gives us a way of dealing with Laplace transforms of certain definite integrals, which is actually fairly useful. So let's see here, this first example, we'd like to find the Laplace transform of the integral from 0 to t of tau sine of tau d tau. Okay, and this fits the form of this integral right here. It's an integral from 0 to t of some function of tau. The function of tau is tau sine of tau. So according to, let's go like this. According to this result, this should equal, now let's write it again. Integral from 0 to t of tau sine of tau d tau is equal to the Laplace transform of the integrand. So the Laplace transform of t sine of t, and notice my tau's become t's at this step, or sorry, s. Yeah, no, that's fine. Yeah, t sine of t, they become t's here, over s. Okay, but what is the Laplace transform of t sine of t? Well, I don't need to evaluate that directly because, again, remember, we have this result here that tells us how to deal with the Laplace transform of a power of t times some function of t, which is what we have right here. So this would equal negative d ds of the Laplace transform of sine of t, and then this is still over s here. Okay, this is equal to negative d ds. What is the Laplace transform of sine of t? Well, we know this one already. It's equal to 1 over s squared plus 1 squared, or just 1, all over s. This is equal to, if I took the derivative of this, which is a quick application of either the power, or sorry, quotient rule or chain rule from calculus, this becomes 2s over s squared plus 1 quantity squared, and again, it's all over s. Canceling those s's, I get my final answer of 2 over s squared plus 1 squared. Okay, so again, just to reiterate on what our theme is here, we're using these operational properties to avoid having to use the definition of the Laplace transform directly. And even though this took a few steps, this was a pretty painless process. Let's do another example. This time we want to do an inverse Laplace transform. Now, this, if you notice the form of this, the inverse Laplace transform of some function of s over s. It turns out that this is really useful whenever we want to evaluate the Laplace transform of some kind of rational expression that has a power of s. Notice we could do this with partial fractions. We've already dealt with that kind of a thing before. But this theorem, this little result that we have, allows us to avoid having to deal with partial fractions now. So to see how that works, before I deal with this guy, I'm actually going to start by dealing with a very similar looking inverse Laplace transform, 1 over s times s minus 1. So I want to start by looking at what happens if this power is equal to a 1. Okay? Notice I could rewrite that function in there this way. 1 over s minus 1 over s. Okay? And the reason I'm doing that is because now it looks like this, a function of s over s. This function of s here, this capital F of s, relates to this f of tau in that it is the Laplace transform of f of tau. So looking at this, what is 1 over s minus 1 the Laplace transform of? It's the Laplace transform of 1 or of e to the t. So that means that this is equal to the integral from 0 to t of e to the, I have to use tau now, d tau. Okay, of course this would just be equal to e to the tau from 0 to t, which is equal to e to the t minus 1. Okay, now notice that's not the answer to our question because we have an s squared here, not just an s. But now I can use this result to find that answer. So now let's look to this guy right here. inverse Laplace transform of 1 over s squared times s minus 1. Notice this can be written this way. 1 over s times s minus 1 over s. Notice once again, I've put it in the form of a function of s over s. But this function that's up here in the numerator is the same function that I already found the inverse Laplace transform of over here. So we know that this guy is the Laplace transform of e to the t minus 1. And I can use that result here in conjunction with this result here. This will equal the integral from 0 to t of this function, but in terms of tau, e to the tau minus 1 d tau, which is equal to e to the tau minus tau from 0 to t. Evaluating this at t gives me e to the t minus t. At 0 gives me 1 minus 0, which is just minus 1. And there you have it. Again, we could have used partial fractions, but we got to dodge that by using this result. Okay? We have one more operational property to talk about, which we'll do in the next and final video.